So I'm Jonathan Mugan from Deep Grammar. We do grammar checking, but I'm not going to talk about grammar checking today. Today I'm going to talk about how we can go from symbolic and sub-symbolic natural language processing like we're doing today to actual real understanding. Now, spoiler alert, I don't know how to do that, but hopefully I'll point to some ideas and give you a sense of what's possible now and point you to some tools that you'll find helpful right away. So it is not my aim to surprise or shock you, but the simplest I can summarize is to say that there are now machines in the world that can think, learn, and create. Moreover, their ability to do these things is going to increase rapidly until in a visible future. The range of problems they can handle will be coextensive with the range that we can handle as humans. So this was Herbert Simon in 1957, and this is where we are today. Siri, I need you to start understanding me. I'll make a note of that. Yeah, you better make a note of that. Got it, of that. And so Siri made a note of that. And this is what we have with Siri. So we had that conversation this morning, that mock-up conversation, so we all know that that's not really possible. We all know that computers have no idea what we're talking about. They're just doing the best they can by hacking over symbols and different things that they can point to. And so this is the problem, right? There is no actual understanding in computer science of how language works, or, I mean, there is some understanding, but no understanding of how to code into a computer how to actually enable them to understand our conversations. AI has gotten a lot smarter. We have deep learning, and that's made huge strides, not so much in natural language processing as it has in computer vision, because computers still can't read or converse intelligently. So in order for a computer to really be intelligent, for we can talk to it, right, it needs to be able to answer these kind of basic questions that a 4-year-old can answer. Like, why can you pull a wagon with a string and not push it? Why is it unusual that a gymnast competed with one leg? Why does it only rain outside? These things require a model of the world that just doesn't exist now for computers. If you put a book on a table and you push it, what happens? And if Bob went to the junkyard, is he at the airport? These things are also amazingly obvious to us that we don't even know how to tell a computer that they're true. And this is because we understand language through interaction with the world. So when someone says chicken, I know what a chicken is because I've had experience with chickens in my life, in my interactions with the world. And so when someone else points to chicken, that isn't just a symbol, it's a pointer into some huge amount of experience that I've had in my life. And so that's why we can both have conversations, is because you and I have had very similar experiences with chicken, at least enough to where we can communicate. And this is what computers need. Computers need this, and we don't quite know how to do this, but there have been two paths to try to give computers some semblance of conversational ability so they can understand. So the first path is a symbolic path. This is what they started back in the 1950s. So you start with meaningless tokens, manual representations, then you build world models, and you merge those representations together. That's one path to computer intelligence from where we are now. That's one path I'll discuss. The other path is the sub-symbolic path, the deep learning path, the neural network path. And this has taken the form of like word-to-vec, sequence-to-sequence model, question answering, and external world training. So in this talk, I'll take you very quickly through both paths so you can get a sense of what's possible now. And hopefully in your lives, you can see where you could plug in and do some research and maybe get some benefit. So we'll first start with the symbolic path with meaningless tokens. So this is when I first learned that this is the state of the art in natural language processing, I was very depressed, right? So we treat documents as simply bags of words. So what we do is we represent dog bit man with the same way as man bit dog. We just count how many times each word occurs. So you consider a vocabulary, which in English, a common vocabulary might be 50,000 words. You put aardvark, which is a little animal, at position 0, 8 at position 2, and maybe zoo at position 49,999. You get this big long vector, and this is your representation of man ate dog, and man bit dog will have the same vector, or dog bites man, and man bites dog. And so this is called a bag of words representation. We put it into a vector. We have a 1 at aardvark if we're talking about the sentence, the aardvark ate the zoo, another one at 8, and then another one all the way at zoo, couple ones for those other words in between, but for the most part, we have a very sparse, long vector, and this is supposedly what this means, or at least as far as a computer is concerned. And we can do a little better. We can count how many times aardvark occurs, and so we can do what's called term frequency. So we count how many times it occurs, so the aardvark ate the aardvark by the zoo. We have 2 for aardvark, and 1's all the way across. So this is, a lot of natural language processing is done with this. You can compare documents this way. You can go a little bit more sophisticated with this route. You can give rare words a boost, because aardvark, I don't think I've ever even seen one. They're not very common in English. And so you can multiply each entry in this vector by a factor of how common the thing is. So if a document does talk about aardvarks, well, that's pretty significant, more significant than if the document has a lot of the words "and" in it, because "and" is a very common word and doesn't mean a whole lot when you're talking about discriminating documents from each other, or comparing documents, right? Because maybe we want to know all of the different clusters of documents. One common thing is in law, you want to be able to do discovery, which is all of the things relevant to a case, or you want to find all of the legal documents of a particular kind, and so you might give rare words a boost so you can find the documents that you care about. Right? And so this thing we multiply by is inverse document frequency. What you do is you count the number of times your word occurs in your corpus. You may have a whole set of legal documents, 10,000 or so, and then you just multiply by the number of documents divided by the number of times that term occurs, take the log of it, and then you now have something called TF-IDF, term frequency inverse document frequency. And this is one of the basics of natural language processing, and it's one of the workhorses. So now if you have the sentence, the aardvark ate the aardvark by the zoo, you get 4.6 for aardvark, because not only does it occur twice, but aardvark is pretty rare in your corpus. And so if you're finding documents and aardvark is something you care about in the odd case, then this document is going to be very relevant. Okay, and this is called a vector space model, a bag of words model. You can throw these vectors into any classifier if you want to classify documents based on sentiment or anything else, to which ones are about aardvarks, which ones are about rare animals. This will allow you to do that. So our next step towards moving on the symbolic path is we can do this thing called topic modeling, which is if we have a whole bunch of documents and we want to start off, what's in these documents? We can do something called topic modeling, which gives us a sense of the cluster of the kinds of topics that are in documents. And you do something called latent Dirichlet allocation, LDA, and you pick the number of topics. So ahead of time you say, you know, I care at the resolution of about 10 topics. And then you can learn this distribution, which is each topic of these 10 topics, and you don't know what the 10 topics are initially, you just guess there are about 10. Each topic will become a distribution over words. So if one of your topics is small animals, then you'd have aardvark and chicken might be a common thing. If another one of your topics is law, then you might have tort, or lawsuit or judge as a common word. And then each document then becomes a distribution over topics. So if you have a lawsuit relating to a zoo, it might have a lot of the small animal words, and it might have a lot of the law words. So it would have like a lot of those distributions. So this is called a latent Dirichlet allocation. You can run this easily in GenSim with online software. You just plug it in. In fact, there is some really great visualization tools available in Python, something called PyLDA-Viz. So what I did is I took all my tweets and I ran them through, and you get these nice little blobs here, and these blobs represent the different stuff I talk about. And if you look at one blob here, 4, you see the most important words. I don't think you can quite read that, but the most important words are like movie, watch, wine. And so sometimes I tweet about movies I like. That's one of the topics I tweet about. And so this corresponds to the movie topic. Now, the great thing about LDA is I didn't know ahead of time which topics it was going to find. This is just one it found. And it's a really great, LDA is really useful if you initially want to just get a sense of what's in your data. And then you say, okay, there's 10 topics, and then it'll print out the most common words of each topic or the most representative words of each topic, and then that gives you a good sense of where to begin when you're doing data science in natural language processing. Okay, so the next thing is sentiment analysis. So how does a person feel about a particular topic? So a lot of times people will write Well, actually, we saw this morning in the Cambridge Analytica. When someone's writing online, are they pro gun control or anti-gun control? You might want to know how these things work, or you might want to know, is this person pro automobile or anti-automobile? Do they believe in public transportation? That kind of thing. So we can do sentiment analysis using the TF-IDF I talked about earlier. You can just take your word vectors, throw them through a classifier. If you've labeled some as positive and some as negative, that can work. Another thing we can do to get a smidge closer to actual meaning is assign words sentiment values. So you have this big dictionary of words, and you say, okay, happy, that's positive, +2, joyful, that's +2, pain or painful, that's -3, and you just have somebody go in and list all of these 50,000 English words as either positive sentiment, negative sentiment, or no sentiment. And then you can also do a little more sophisticated, and if they have the word not in front of it, then you flip the sentiment. So if you say it's not joyful, that would be, since not is positive, you just, since joyful is positive and not is a flipping word, you just flip it. And so this is a sentiment dictionary. One common sentiment dictionary is Vader. So this is based on using Twitter. They had a bunch of people go through and label things on Mechanical Turk, so this is useful, and you can just download it. And so if you have the sentence, I went to the junkyard and was happy to see joyful people, that will be positive because happy and joyful are positive. Now, this isn't really understanding, but it's getting one step closer because we went in and mapped positive or negative sentiment to these symbols. It's still pretty rudimentary, but we're getting somewhere. Okay, so that is the meaningless tokens. So we started off with meaningless tokens. We did TF-IDF. We did sentiment analysis. We gave a little bit of meaning with the sentiment. But the next level is creating manual representations, going in and assigning what symbols mean by hand, just going in and saying what the symbols mean. So, and then you can store meaning as relationships between these symbols. So let me give you an example. Let's say that you want to know, you're watching Twitter and you want to know, okay, I want to sell stuff to people who are interested in tires. Who's going to buy tires? And so how could you tell a machine to do that? You can't just tell a machine, okay, look out for anyone who's interested in tires, because computers can't read. They can't read any of these tweets. So what are you going to do? You're going to create a set of symbols, and then you can map those symbols to what you actually care about. And so in this case, you have vehicle, tires, and Honda Civic. So you say, okay, a Honda Civic is a vehicle, and a vehicle has tires. So if you bother to write this down, then when people say the car, you can map that to vehicle. An automobile, you can map that to vehicle. My truck, you can map that to vehicle. Cruising in my Civic, you can map that to Honda Civic. And you can know semi-automatically, once you've taken the trouble to write all this stuff down, who is actually talking about tires. So again, there's no deep understanding here. The computer is just using the manual meanings that we have assigned to make a decision who might care about tires. So one common way that these things have been written down is something called WordNet. WordNet's probably the most common source of map symbols. So it organizes words into sysnets, which are boxes or groups of words that all mean the same thing. Okay? And then a word can be in more than one sysnet because a sysnet is a unit of meaning. So consider the word bank. So a bank can be a building, it can be a financial institution, it can be the side of a river. These would be three different sysnets. In our case, we have automobile, and we have three words that all go in the same sysnet. We have auto, automobile, motor car. Okay, any of those words, for our purposes or the purposes of whoever wrote down this set of things, is the same meaning. And then we can say, okay, auto has part automobile horn, it has car horn, motor horn. For the use case we saw in the last slide, it has tires. And then you can say, okay, well, an automobile is an instance of a motor car or an automotive vehicle. And as you can imagine, this is a huge amount of work to write all this stuff down. The great thing about WordNet is it's already done this, at least to some degree. An ambulance is a type of automobile. Now, of course, it kind of is, kind of isn't. Sports car and sport car is another sysnet that's like that. And so then this is WordNet, available online to anyone who wants it. And it has other relations as well. Has instance, has member, but it's pretty basic in terms of its relations. But it has pretty good coverage. There's something else called FrameNet. So where WordNet was the meaning of individual words, FrameNet takes that to the next level and says, we're going to care about what are the meanings of situations. So if a computer is trying to understand something, like a child's birthday party, we're going to say that it has a very specific set of things. So in the United States, all birthday parties for children follow the same relative script. There is some sugar source, so it's usually cake or cupcakes. There's some entertainment source, which is usually like a jumpy balloon or a clown or something. And so any birthday party is going to have these slots. And a birthday party then can be represented to a computer as a symbol with pointers to these slots that individuate which kind of birthday party we're talking about. Another one is commerce by, which is a frame. Whenever you buy or sell something, that's a situation that we can represent to a computer with a symbol linked to other symbols. So in commerce by inherits from getting, and it's triggered by words in a sentence. Okay, so if I buy a car, and if I write that down, I bought a car, the word bought would trigger to FrameNet, the commerce by frame. And then I bought something, so then FrameNet would look for the thing in the sentence that was the thing that was bought, and so it would map car to that. Then it would look for the agent, which was me, the buyer. Then it would also look for the seller, but in this case, I didn't mention the seller, so it would just be blank. So this is FrameNet. So we moved from WordNet, which is words, to FrameNet, which is situations. Okay? And so there's something else called ConceptNet, which is the linkages between more common sense things. So my experience is ConceptNet is too shallow and haphazard to be useful, but it's worth taking a look at. And it's not anything against ConceptNet. It's just the trouble of the world is so complex, trying to write everything down is really, really hard. So you can say that it has something like bread is located near a toaster. Well, so think about all of the things in the world that are true at that level. But that actually is something that we've all experienced, and that is the kind of thing that computers need to know. But it also, in ConceptNet, lists a toaster as related to an automobile. And I guess that's true. They are machines. But if you're going to have something like this at this level of organization, it's never going to scale. So this is certainly a big challenge. Now, you can imagine a chatbot saying, okay, I'm going to use ConceptNet for a chatbot. So anytime anyone mentions bread, I'm going to chime in with my world knowledge and say, you know what's near bread? A toaster, right? So that would be a very boring chatbot, but we're starting to get to some kind of common sense reasoning, even if it is very shallow. And there's something else called Yago, which builds on top of WordNet, which we have seen. Yago builds on WordNet, and Yago builds on something called DBpedia, which DBpedia is a machine-readable form of Wikipedia. And this is very useful for anything in Wikipedia like sports celebrities, singers, things in location. It's not useful for bread and toasters. Wikipedia doesn't care about that stuff, but it does care about celebrities and that kind of thing, and it has very good coverage for that sort of thing. So Yago bridges WordNet and DBpedia. And then you can browse this online if you want. So these slides, I don't know if they make them available. I assume they do. But on my website, jonathanmugan.com, there's like a writing and talking thing, and then I've listed all the slides from all my talks. You can go through and just find them there. And it may not be slides listed for this talk, but then it'll be similar to some other talk where you can get all these links so you don't have to try to write them down. And so my favorite ontology is Sumo. So Sumo is very deep as opposed to these kind of superficial things. It organizes concepts down to the lowest level. And so what it says is cooking is a type of making that is a type of intentional process that is a type of process that is a physical thing that is an entity. This is how deep this goes. Now, of course, even Sumo is very incomplete. It tries its best, but the world is just so complex we have a hard time writing it all down. And then there's Yago Sumo, which tries to merge Yago and Sumo. And we've got a ways to go, but there are a lot of people out there working really hard to write down everything that is necessary, and you can take advantage of it pretty easily online. And so below these levels of things you write down, with bread being near a toaster and they're both being machines, there's these things called image schemas, which image schemas are the representations that are postulated to be underneath language. So many of you speak Ukrainian here, I speak English, and it doesn't matter. In image schemas, our language is built on top of these core concepts like containers. So if I put something in a glass and I move the glass around, the thing inside the container also moves. And we need to have these kinds of understandings if we're ever going to learn Ukrainian or English. Another one is physical force. If you push something, and we understand even deeper things, such as she forced me to sign the contract. So, she forced me to sign the contract. We can understand this as a metaphor to the physical schema of one thing forcing another through physical force. And so a lot of people believe that that's how we understand these abstract concepts, through metaphors to these very fundamental concepts. Unfortunately, I don't know of any good implementation of image schemas. Hopefully someday someone will build one, and then we can put, sumo on top of that, and then Yago, and just all the way up. So there is the semantic web, which is trying to put a lot of these things together, but right now it's just, I think the task has been a little too hard. It hasn't gotten a lot of traction. It has gotten a lot of traction, but it hasn't been able to really take it to the next level. Hopefully people are working together to make this whole layer cake thing more usable. I had a really hard time when I got into semantic web figuring out what all these things are about and how they all relate to each other. Hopefully, I think some people are working. There's this thing called JSON LD that's trying to bring these things more streamlined. So that is the manual representation. So when I talk about we're building on top of symbols, we're building manual representations where we're saying, okay, this is what this symbol means, and this is how this symbol relates to this other symbol. The next step is to build world models, which say not only what something is, but what happens in our physical world when there's an event. What is the result of that event? And that's where computers are going to need world knowledge to understand us. So they need this causal models of how the world works, because when we talk to each other, we only say the things that are not assumed to be understood between us. So in a romance novel, there might be two lovers, and you would never read in a romance novel, they looked across at each other across the table with their eyes, and then they pushed the table aside between them, and as they pushed the table, all of the objects on the table moved because they were fixed to the table, and the gravity pushing down did this. So you would never see that in a romance novel, so any computer trying to understand the world through romance novels could never get that level of detail, because we all know that when we push a table, things on it move, and it's an irrelevant detail, and we don't want to read it. And so a computer is going to have to understand these models of how the world works in order to read romance novels, which is, of course, the highest level that we aspire to. So we need to understand how the world changes based on events. So I talked about the commerce by representation in FrameNet, but we need a world model to say, well, after commerce by, there is one person that has something they didn't have before, and another person that has money. And then what does money mean and all of these things? You need to have the dynamics coded in with these representations. And there's a lot of different factors in models. Building models is really hard because the world is so complex, but it's also hard because the model space is so complex. You want the models to be probabilistic, because usually when you push the table, the things move with the table, but maybe sometimes they don't. Maybe they're a weird kind of thing, you're in space and there's zero gravity. That's why you need to be probabilistic, because probability allows us to represent not having full knowledge of the world. And you need to factor the state. So a lot of things like deterministic finite automata factor everything into a state. They put everything together, but of course some things don't matter to other things. So in order to represent a model, we need to break that out and move to things like dynamic Bayesian networks. And models have to be relational as opposed to just first order. As opposed to propositional logic, we need to move to first order logic, which is you define a set of predicates, but the things that can take those positions are arbitrary. You don't merge it all together. Models have to be representing things that happen at the same time. So if something's happening over here and something else is happening over here, you don't want to have to put that all together, multiply it together, and blow up your model space. And they have to represent time, of course. So we've got a lot of work to do, both in terms of writing down everything that matters in the world and getting all of these different pieces together. So that's our world models. And so what we want to aspire to is to merge these things together along the symbolic path into merged representations so a computer can really understand. And so if we've done this, then we can ask a computer, why does it only rain outside? And if it gives the answer, well, a roof blocks the path of things from above. That's the kind of answer. When a computer can give that answer to arbitrary questions, then I know the computer's thinking from first principles. It's saying, well, there's some water that comes down and the roof blocks it, so therefore it only rains outside. And of course, if we're able to specify things from these first principles, we won't have to give it this arbitrary number of facts because there's just way too many facts to ever write down. Another one, so if I ask a computer, explain your concept of conductivity. And I don't understand electricity. I mean, I took the relevant physics class, but I don't, who knows what electricity is. But if it says, if a computer says electrons are small spheres and electricity is small spheres going through a tube, conductivity is the blockage in this tube, how much blockage there is. Well, that's kind of, if I were forced to say how I understand conductivity, that would be the level at which I'd understand it. And if a computer can understand it at that level from these first principles, we'd know that we've made progress along this symbolic path. And then if we can ask it, of course, what the meaning of the word chicken is, a computer can tell you exactly what it can do with a chicken. Then we've gotten something, because what we want from the symbolic path is a computer to be able to mimic what we've gained through our physical interactions with the world. And there is this thing called psych I think it's it was started in Austin, where I'm from, Austin, Texas. And it tries to build in all these representations using first-order logic to start from the very beginning. And it's not clear that first-order logic on its own is enough to really represent all this. And they've been working for 30 years, and I don't know their current state because they don't publish too much, but they haven't made it yet. So, in 30 years, that's a long time. Okay, so that is a symbolic path. And the next path is the subsymbolic path, the neural network path, the deep learning path. So let's talk about that. So a great place to start, if you want to start where the cool kids start, is this landmark publication, Parallel Distributed Processing, Volumes 1 and 2 from 1987. So let's start with Word2Vec. We've probably all heard quite a bit about that. So Word2Vec learns a vector for each word in a vocabulary. So we saw in the TF-IDF representation that if we have a vocabulary of 50,000 dimensions, we have a 50,000 dimension vector. So there is some position 2773, 27,774, whatever it is, corresponds to some word, and the number there corresponds to how important that word is in the document. Most of the positions are 0 because most words won't occur in most documents. Word2Vec learns dense vectors. So it learns a vector of only 300 dimensional, but now you can no longer say what position number 56 actually means. So here's the Word2Vec algorithm. You can think of it as a double for loop. So we're trying to learn a vector for each word that represents the meaning of a word. And I first saw this double for loop through Christopher Moody. So you have your long set of documents, and you go along each word. I went to the store and bought some tacos for my chickens at home, right? And so for every word, you look for the words around it. And you say, I want to make the word vectors for my central word and the words around that be closer to each other. So I move them closer to each other. And then all of the other words in my corpus, or all the other words in my vocabulary that aren't in that window, need to be further apart from the central word. And then I move over to the next word and look at the 2 words on the left and 2 words on the right, move them closer together, move all the words farther apart. Move over to my next word. Do that same thing until you get tired, is basically the algorithm, right? So for each word, W1 in the set of documents, for each word around W1, you move the vectors closer together, move the other ones further apart. And there's some technical things. There's actually 2 vectors per word because you don't want a word to show up near itself. But that's the basic algorithm. And what you get out of this is something pretty cool. So you get the famous result that if you take the vector for Italy and subtract the vector for Rome, you get some other vector, 300-dimensional vector. And if you take the vector for the vector for France and subtract the vector for Paris, you get some vector. And those two vectors that you get, the resulting vectors, are actually pretty close to each other. So somehow in these 300 dimensions, it's encoding capitalness as a feature. And the same with king minus queen is equivalent to man minus woman, or close. And somehow it's incorporating man-womanness in this. And in fact, this is one of the ways that they evaluate how well a vector learning algorithm works, is they give it some kind of like analogy test that they give the US high school students and see how well it can do. So there's some kind of meaning here, right? And the famous phrase is, you shall know a word by the company it keeps. And this is kind of true, as we've seen, although it's not completely true, because we've seen you don't write down everything we know. We only write down what doesn't need to be expressed. So these things that a 4-year-old knows, we don't bother to write down. So you can't learn the full meaning of a word that way, but you can learn some neat stuff. The words are grounded, but they're only grounded in other words. Okay? So the next big thing that you guys may have heard about is sequence-to-sequence models. So this is where you take one sequence and then predict another sequence. And so this shows up in machine translation. You're translating English to Spanish. You have a whole bunch of sentences in English, and for each sentence you have the equivalent word in sentence in Spanish, and you translate them between the two. And you teach a deep learning algorithm to do this. This is generally done using a recurrent neural network, and we'll see an example here in a second. And I guess we'll see an example right now. So the patient fell. So what you're doing is you take the, and sequence-to-sequence models implicitly learn word vectors as part of the algorithm. So you take the, and you generate a state, and you just use its current word vector. Remember, we initialize all these things, all these word vectors initially randomly. So we have some random word vector, which is now the state H0. And what we do is we have our current neural network sitting right here that takes the previous state, which is a 300-dimensional vector, the word vector for patient, and combines those two together into some new state, H1. Then we use the same set of parameters here to combine the previous state and the new word vector for fell into some new state, H2. Then we, of course, do the same thing again, take H2 and combine them with period into H3. So H3 is now a 300-dimensional vector that, in a sense, represents the meaning of this sentence. So it's like a hidden Markov model, but it doesn't make the Markov assumption, and it benefits from a vector representation. So now to do machine translation, we start off with our H3, which is our previous final state of the sentence, and we generate a word, L. With our new, we have a decoding now. We've encoded it using recurrent neural network. Now we're going to use a different recurrent neural network to decode what we just encoded into Spanish from English. So we generate L. Now with our recurrent neural network, our different recurrent neural network, we take the previous state and the previous word and generate a new state. And basically this is, in its most simplest form, it's a matrix multiplication time this vector plus another matrix multiplication time this vector, add them up. And that's just a vanilla recurrent neural network. Of course, there are more advanced things like LSTMs, but at the basic, that's what's going on. Then from here, we have a softmax, which is a classifier that generates the next word. Of the 50,000 words, let's say we have 50,000 words in Spanish as well as English, and we have a 50,000 decision problem. Generate paciente, and then we do the same thing. We run our neural network here to generate a new state from this previous state, and from this word, and we generate cayó, and we keep going until we hit a stop symbol. And this doesn't seem like it should possibly work, but it does, because we have so many different sentences in English translated into Spanish. Now, of course, humans had to do this initial translation, but then a computer can learn 5 minutes. A computer can learn to mimic this like that. All right, so, and it keeps going. Now, you can then do captioning like we've seen. So you take a convolutional neural network. This is my son. He was all wet. You take a convolutional neural network, take the top level, you get a vector. And then, we all know now with a vector we can do a decoder and decode that in a sad wet kid. And that's how these image captionings work. There's no understanding here. It's just a lot of different computer power. So there's this thing called attention. So when you're looking at these vectors as they're 300-dimensional, you might wonder, well, how can you keep encoding more and more stuff into a same fixed amount of vectors? So you allow the vector, when it's trying to make a decision, like when it's trying to decide, should I decide Caillou here out of 50,000, you can not only look here and here, but you can look at all of these previous things, and that's attention. And in fact, this attention, and I can't go into detail because we have like 4 minutes left, but this attention is what's used to do question and answering. So you have a story here like Bob went home, Tim went to the junkyard, Bob picked up the jar, Bob went to town. The question is, where's the jar? And because we never put down jars when we pick them up, we know that the jar is in town. And they can do this. Computers can do this. They can answer questions like this, but there's no understanding because it's just thousands upon thousands generated stories like this, and it's just doing a softmax over the symbols. But it is really cool, but we're still not understanding. So we're down now. What we're going to need is some kind of external world training, right? Because we can't just learn on the symbols. We can't learn on generated stories because generated stories don't have enough detail that a 4-year-old needs to really understand something. So you can have machines that must train in simulations like our own. Maybe it could be in a simulated environment. Maybe it could be with a robot. But they need to understand chicken because they've experienced chickens, or maybe in simulation they experienced something like chickens. And this is what we're going to need. And in industry, they are working on this. There's some really cool stuff with OpenAI, and in academia, they've been working on this. And they have the iClub, which is it's a little dude. He's really cool in Europe, little robot. I think he came out of Italy, maybe. I don't know where he came from. I'm sorry, don't go in it. But he came from somewhere around here. And so maybe if Amazon Alexa had a camera, she could look around, and maybe she doesn't need to physically manipulate things in the world. We don't know. If you need to physically manipulate objects in the world to understand, or what you need to really get this kind of understanding, but we need to get a lot closer than what we are today. In fact, as we go, we've seen both on the symbolic and the sub-symbolic paths. We're getting there, but we still have a long way to go, and we can do some cool stuff, but it's all basically hacks. There's no understanding from first principles yet. And in fact, one thing as a lot of us here are entrepreneurs, like, what is the simplest commercially viable task that requires actual understanding? Because if we can pinpoint some task that we can actually start getting our teeth into that actually requires real understanding, then we can attract funding. We don't need 30 years. We need maybe 5 years, and this might be viable. One viable way to get this done. So that's my talk. Thanks for listening.